Okay, friends, from Center of Excellence in Advanced Manufacturing Technology at IIT Kharagpur, I'd like to welcome you all in this mega webinar series named as the Saturday Manufacturing Talks, which we started in the month of March of 2021, aiming to disseminate knowledge in the field of the manufacturing across different components. We had the eminent speakers from industry, academia, India and from abroad, speaking different aspects of the manufacturing, like the additive manufacturing, robotics, supply chain, automation, industry 4.0, artificial intelligence. So today we are fortunate to have Mr. Amish Thakkar, who will be speaking about the how IT concepts is changing the world, and it is playing an important role in the field of the manufacturing. So I'd like to go through the, read the brief bio sketch of Mr. Amish Thakkar. Amish Thakkar is presently the Vice President of Infosys. He heads the Microsoft Business Applications practice for the EMEA region. He has worked with clients in many different countries across industries, helping win large transformational deals on big applications. He has worked as an executive with more than 23 years of experience in IT and business consulting with Fortune 500 clients from different industry sectors: automotive, consumer goods, retail, utilities, and pharmaceuticals. He has led transformational engagements in Germany, UK, Ireland, India, Netherlands, Poland, Russia, and Canada over the last 23 years. Amish is Bachelor of Technology degree holder from IIT Kharagpur and postgraduate diploma in business management from XLI Jamshedpur, India. Thakkar has served since 2019 as the Associate Vice President, Senior Practice Engagement Manager, EMEA, in the Microsoft Business Application Services practice at Infosys. Prior to rejoining Infosys, Thakkar spent 12 years in Capital. So let us hear from Mr. Thakkar on this interesting topic, that importance of IT sectors in the field of manufacturing. Mr. Thakkar.
Thank you, sir. And it's a pleasure coming here and presenting on this topic. IIT Kharagpur always evokes very fond memories for me. And I see one of my professors from whom I learned a lot, Professor P.K. Mishra, is also there as one of the participants. So I'm looking forward to talking to all of you. So I prepared a few slides and I'm going to share my screen now. Okay, are you able to see the screen with the title?
Yeah.
Okay, yeah. So in terms of the agenda, what we will do is we will go through these following points. I'll talk about some of the technological changes and adaptation, how software is a bit different as a soft technology. And this also gives software certain disruptive properties which can be leveraged. So we will then delve a little deeper into how unpredictability is sometimes a strength when it comes to software, and how the software revolution is different from previous technological revolutions. I'll finally conclude with one example of how IT interfaces with manufacturing and how this can be leveraged with a specific example. Then we'll close with certain references. And please feel free to interrupt me if you have any questions. In terms of flow, these two topics, unpredictability as a strength, what is different this time, I might skip a few slides so that we can spend a little more time on the specific examples. But let's pace it as we go along. Okay. Now, The first iPhone was invented in 2007. Before that, if you recall, we had smartphones with physical keyboards. Some of you may have also used Blackberries, which had thumb wheels for scrolling. We used to use those thumb wheels for scrolling between emails. And the BlackBerry also had a very rudimentary browser. Now, when the first iPhone was launched, somebody asked Steve Jobs that users are very used to physical keyboards and you have only a touch screen. There is no separate keyboard. So do you think users will accept this? And his reply was very terse. His reply was, they learn. Now, we always think that products have to be adapted to human needs. As human needs evolve, products have to be adapted. But what we tend to forget is that users also adapt to products. And once the users have adapted to products, they get so used to working with the new product, working with a different interface, that they practically forget, they change their way of working, their way of using the interface. And because they forget this, they never realize that they'll be changing again in the future. So they think they always behaved like this and that will never change. They forget the fact that they have changed in the past and there'll be many more changes going forward. Which leads us to the last point, that sometimes the changes that we are making in adapting to products are unexpected because we don't remember the past changes. And these unexpected changes may sometimes appear to be regressive. They appear to be steps backwards rather than steps forwards. But we'll see how these changes are always having a positive trend at least. Individual steps may be backwards, but overall there's a very clear positive trend. Okay. Now, when we talk about transformative technologies in the history of human civilization, we could talk about a handful of technologies, maybe invention of agriculture, the steam engine, electricity. But many of these were hard technologies, and some of the soft technologies which really changed human civilization: written language, money, and now software. When I say soft technologies, it essentially means that there are many ways of embodying these soft technologies in a physical form. For example, if we are talking of written language, you could write with a piece of stick on sand, you could write with chalk on a blackboard, or you could write with pen on paper, and even on a computer with a keyboard. So there are many different ways in which you can have written language embodied in a physical form. Pretty much the same thing applies to money. You have coins, you have notes. Earlier, there was a barter system, so people traded spices, prisoners in a prison. They even trade cigarettes as a form of currency. So the many manifestations of money in the physical form. And software is another soft technology, which we'll now delve deeper into. And this distinction is important. We'll soon see why. Now, when we talk about an IT revolution, a software revolution, there are aspects that we see, and there are huge changes that we do not see. Just like an iceberg, a lot of the changes are below the surface. These are very small effects which accumulate into a massive revolution. And we tend to miss this. We tend to focus on the seen part, but we tend to miss the huge changes that come until they hit us. I'll explain what this means. Let's take, say, a 15-year-old programmer today working on a transformative open source project. So he's contributing code to an open source project. The metrics as they stand today, economic metrics, the labor statistics do not reflect this labor because he's a 15-year-old, he's not an adult yet, so his efforts are not captured in the labor statistics. The economic metrics will probably say, okay, the economic usage is just the laptop and internet connection. That's what the economic metrics will measure. But what is the real impact that this 15-year-old is having? The real impact, if he's contributing to a transformative open source project, he's operating at the level of a 22-year-old with a college degree, holding a good job. And this 22-year-old would probably have spent at least 4 years going through college, spending at least in the US, at least $100,000 going through college. But this 15-year-old teenage programmer without a college degree has leapfrogged 7 years into the future because he's contributing something to an open source project that somebody equivalent to this 22-year-old with a college degree would be contributing. Sometimes the real impact may be much larger. Some of you may remember there was a software called Napster, which was eventually shut down because it resulted in a lot of music piracy and lawsuits, but it disrupted the music industry in a huge way. It brought music online in a huge way. Now, Napster was actually started by a teenager. So you can imagine the impact that the teenager had by creating Napster. Now, that's where the point of small changes that accumulate and result in a huge revolution becomes significant. Most of you will be familiar with Moore's law. Moore's law is about how many transistors can be packed into a silicon chip of a particular size. And Moore's law states that the number of transistors that can be packed on a chip of a certain size doubles every 18 months. And this has held true for quite some time by and large. Now, if we were to change this equation slightly, let's use the same concept of Moore's law. But what happens when scientists, instead of driving raw performance by packing more and more transistors, what if instead they focus on lower cost and lower power consumption? When they do that, they improve accessibility. Suddenly you find that the power consumption and cost has reduced, so many people can afford different devices, which has been one of the reasons for smartphones becoming very successful. So many of us carrying smartphones today. And that is what is also leading to the potential of Internet of Things, where we are talking about embedding devices in various different items today. Potential of IoT could be several $1 trillion, and all of it needs software. So that's the kind of spectrum that we are talking about when it comes to software. So let me go to the next slide. Let me take a very specific example. When we talk about the seen and the unseen, I mentioned that the large changes are unseen. Most of us are used to taking Uber or Ola. When this first started, app-based taxi ordering, the whole thing seems so trivial. Instead of ordering a cab on the street, or in some of the Western countries, you would maybe call someone and order a taxi. So the first order effect was simply there was a convenience in procuring taxis. That's what it amounted to. There was a small app, probably a bit buggy, which allowed you to procure taxis through the app. Then they built payment features. So you could now pay with a credit card through the app or through Paytm, or you could even pay cash to the driver. So there was a convenience in paying and procuring. All of it, I would say, pretty predictable, more like a first order effect. But how transformative this has been as the processes and systems matured. Let's look at some of the other effects that emerged. And some of this we could have envisaged, some of this even the founders of these apps would never have thought of when they first started this. The thinking evolved as the app popularity grew. Now, I mentioned about ordering cabs. So typically in a place like London, you would call and somebody would look at their entire taxi fleet and identify, okay, for this address, this is the nearest taxi. It would be a radio taxi, would radio the taxi driver who would come and pick you up. Now, when you started ordering through the app, you didn't need anybody at a call center. You didn't really need anybody to identify which is the nearest taxi and actually radio the taxi driver. So it eliminated the role of these human dispatchers. Further, again, taking an example from London, London has what is called black cabs or hackney carriages, stringent requirements for qualifying as a black cab driver in London. It used to take the drivers 2 to 3 years to qualify because the requirements were such they had to like maybe know several thousand roads in London. So if I ask a black cab driver, okay, I want to go, I'm in Earl's Court and I want to go down to the Wimbledon Stadium, he would know exactly which routes to take, what would be the shortest path, probably what would be the traffic conditions at that time of the day, what would be the main landmarks that we would pass through. And I wouldn't even actually have to give him the full address. I could just give the postcode and they would be able to take me to that road. So the taxi driver, the black cab driver had to memorize all of this, and that entire process took 2 to 3 years. But suddenly these app drivers started using GPS, and that lowered the expertise level required from these drivers. Now, as more and more taxis were ordered through the apps, we had GPS tracking. We could see which drivers actually took an efficient route. Uber or Ola, these cab companies could see that which drivers really took the efficient routes, avoided traffic, made sure the customer had a good experience. And they could identify the good drivers. And the drivers had ratings. Now, typically, earlier when you ordered taxis, you had to be sure that it was a regulated taxi and the taxi was from a good brand name company so that you could trust the taxi driver, both from a safety issue and also giving you a good ride experience. All of that effort on branding regulation was no longer required because there was GPS tracking and ratings which provided you the data. So all the branding, marketing effort, advertisements, that cost was cut out. Now, coming to the second point, lowered expertise for drivers meant the driver supply increased. And because the driver supply increased, more vehicles, more underutilized vehicles, people who could never have qualified as black cab drivers, they could suddenly come on road as Uber drivers. And underutilized vehicles came on road. So it increased the utilization of these underutilized vehicles. Now, because the supply increased, many people started adopting a carless lifestyle. If you look at the US, most places in the US, you need a car. But suddenly, with the availability of Uber, many people did not need a car anymore. And they could even if they did not own a car, they could afford to live a bit far from their workplaces because they could catch a quick Uber. This actually resulted in reduced requirements for road networks because now not everybody needed a car. The urban landscape was reshaped because earlier people who had to rely on public transport had another mode of conveyance to travel to work. So they could count on Uber. And even if there was no other public transport, they could live in a different area. They didn't have to necessarily live close to a subway station in New York. Many insurance models were revamped. So insurance companies, they sold car insurance. With each car sale, every driver had to have insurance. Now that was no longer required. But these rideshare drivers needed insurance. So all these insurance models had to be revamped. Further, the insurance companies could even tweak their pricing based on the driver ratings. Let's say a driver who has very good ratings because he's a very safe driver, they would charge him a lower premium because now they have driver specific data. Some of them even had a provision that if a particular driver agreed to fix a small device in the car, which would pretty much track the speed of the driver at every point, track what the driver was doing, then they would agree to lower the insurance premium because they had much better data on the driver. Taking this forward, this model developed into delivery services. Uber resulted in Uber Eats, and people started ordering takeaway food, which changed the restaurant experience. And I myself faced this actually a few weeks ago. I was in Stuttgart, Germany on a Friday evening, and I stepped into a restaurant. Because corona numbers were high, I was careful not to go to a place that was too crowded. So there's this big restaurant with adequate spacing between tables, not very crowded. I comfortably walk in, and the food, I ordered the food and it took a very long time to come. When I asked the owner, I said, "What's wrong? Do you have a problem with the kitchen? Because there are not so many guests here. So how come it took so long?" And it was like, "No, it's these app-based orders. I'm flooded with too many app-based orders, so I'm struggling to cope up." And what I had seen from the outside was, okay, there are not so many customers and I can walk in, I'll probably get something quickly. So the whole experience changed. A dimension was introduced, which we have not foreseen. Now think of it, when Uber first started as a buggy, trivial app, all these second and third order effects we would never have envisaged. So when certain key component technologies are in place, we suddenly leapfrog to the next level of experience. And these key component technologies accumulate over a period of time. That's what I was talking about. Small changes, invisible, and suddenly result in a big revolution, which right here you see it as one example. Now, the author of Dilbert cartoons, Scott Adams, has written a book, Win Bigly, where he talks about, in his free time, he used to try various small experiments, various projects, and he talked about one experiment that he tried early in his career where people could record videos and upload it on a website and others could view it. The website was not YouTube, and his project failed. And his project failed because at that point of time, not everybody had a Wi-Fi connection, not everybody had these smartphones, so not everybody really recorded videos. You probably needed camcorders at that time. So all these surrounding technologies were not in place. But when the surrounding technologies were ready, YouTube suddenly came and changed the landscape. Now, how software really results in a reversal of certain relationships. In the US, most places, car is pretty much a way of life and smartphone is an accessory. So when Uber app came, most of us probably thought that, okay, this smartphone is an accessory and most of the value is in the car. Just a little bit of the value created is in the app. But it's actually quite the opposite. Most of the value happens to be in the software because many people started adopting a carless way of life. Earlier, when a teenager grew up and he owned his first car, he thought this was freedom. Finally, he was free. He didn't have to rely on his parents to drop him and picking up from various places because there was not much public transport. But now suddenly the concept of freedom is, I am free, I don't need a car, I go by Uber. And this very concept of freedom changed with what was a seemingly trivial app. Now, amongst the soft technologies, I talked about money and language. Software takes us even further because money, you have seen how software can be embodied in the form of cryptocurrencies. Language, you can have simultaneous translation using software. So software will actually take us even further than money and language did as soft technologies. Much like compound interest, we tend to underestimate what the impact will be in the long run, but we overestimate the impact in the short run. And we'll see what this means. But this is probably something that led to the 2000 dot-com bust because we were expecting a lot to happen with software too soon. We were expecting online ordering of groceries, which did not take off in 2000, but it's very normal today. So Now, because we have seen so many changes and we have adapted to these changes, as I mentioned early on, we pretty much forget that we adapted to these changes and we behave as if it's normal and nothing much will change. But actually, very profound changes will come going forward. Because software has many component technologies in place now, installation largely done for many areas, and we are in what is essentially a deployment phase. Now think of it, software is often hidden. It's embedded. You don't see it, so you tend to overlook the effect. Let's look at fields like genomics. It's not like there have been huge discoveries in biology which helped us to decode the entire genome. It was advances in computer technology which enabled us to process all the data to decode the genome. Nanotech, it's not some very big discoveries in material science. Instead, it's the software which enabled these technologies. 3D printing drones, again, yes, certain changes in manufacturing techniques, but a lot of it was the underlying software which enabled us to get into 3D printing and drones. Financial innovations today, there's an entire field, financial engineering. Pretty much all of it is driven by software, new financial products, derivatives. I talked about the insurance models. All of that is mathematically modeled with software. Google bought a company called Nest, which enables smart home capabilities. And one of the features of Nest is that it reduces heating costs by helping to determine at which level the thermostat should be kept. Now, there have not been new discoveries in thermodynamics which enable us to identify exactly at which level the thermostat should be set. It is the underlying software which enables us to process the data and come up with this optimization. Now, another thing that has happened since 2000 is that the software could be decoupled from hardware. What it means is that earlier software was very dependent on hardware. Now you can even have virtual machines which essentially simulate the hardware to run any kind of software. Until around 2000, the idea of software was that we looked at a specific problem. If a large company had trouble balancing its books, you improved their accounting software. If a large company had problems with tracking inventory on a shop floor, you established a proper warehouse management system. You deployed that so that they could identify exactly what was kept where on the shop floor. But we never explored the frontiers of possibility with software. We were just focused on specific problems, and that started changing sometime from 2000 onwards. Now, this kind of underestimation, it had parallels in previous technology revolutions also. I talked about the discovery of the steam engine. Nobody could have really foreseen how the entire urban landscape will change with the discovery of with the invention of the steam engine. But it happened, and a similar thing is happening with software. And yet there is something extra, something very unique to software, because software is upending established institutions. What does it mean? Earlier, pretty much the future was determined by older generations. They could borrow from the future from. So let's take fossil fuels, for example. Older generations could use fossil fuels and improve their lifestyle. And pollution was not a big concern, at least till some time back. The costs of pollution have to be borne by the future generation, which had no say. Some of them were too young, some of them were as yet unborn. So pretty much the future generations could determine the direction the civilization could take by borrowing from the future. But today, young kids can lead software revolutions. They are not bound by existing institutions. Nobody can stop them from setting up a startup, and they operate at the margins. Now think of it, the whole thing is not a political force. There could be small messaging apps, there could be photo sharing apps. All of that seems so trivial. Facebook started as a network for connecting friends. And today, there is so much of political discussion around Facebook. Nobody saw it coming because it was all happening under the surface. But it suddenly becomes a political force to reckon with when there is so much of data on Facebook. So the whole change starts as a technological change, not as a political change, which means there are no real opposing forces. Nobody realizes. It's a commercial change, not an ideological change. Unlike previous revolutions, you could say the hippie revolution, where it was such a visible change, but here it's different. It is not driven by paperware, it is driven by software. So if somebody doesn't have a college degree, doesn't stop him. And again, think of it. This is a generation which is now talking about earlier financial autonomy. Previous generations are willing to start with debt just to get a college education and eventually home ownership, and over a 30 or 40-year period, they would pay back their debt and achieve financial autonomy. But now the generation is talking about starting with financial autonomy. So it's a complete reversal led by many unseen changes. So I'm going to pause here if there are any questions before I proceed further.
No, please go ahead. Actually, the question and answers may be there at the end.
Okay, yeah, that's fine. Okay. Now, let's take some specific examples of how the IT revolution is very different, and it is not so predictable. This is a revolution where actually inventing the future is much easier than predicting it. One of the reasons being that when you try to predict the future, if the future is beyond the bounds of what you can envision, as we saw with some of the examples, you're actually limiting the future. Specific examples, there used to be a chain of bookstores called Borders, based in Ann Arbor, Michigan, headquartered there, and they had bookstores all over the US, UK. They sold their online business to Amazon because they said, we are only interested in physical bookstores. Online sales of books are not strategic to us. As Borders was filing for bankruptcy, Amazon was simply changing its website to highlight Kindle ebooks. Amazon had launched Kindle ebooks and they were making changes on their website to bring the focus to Kindle ebooks, while Borders was going through bankruptcy proceedings. Netflix and Blockbuster, probably a very familiar example already. Which are the biggest music companies in the world today? Apple's iTunes, Spotify, Pandora, which are essentially software companies. They didn't start as music companies, but the traditional music companies upended by software. Zynga and Rovio. Nintendo is the video game company. Rovio is the company that started Angry Birds. So Zynga and Rovio are bigger than Nintendo. Disney, famous animation company, had to buy Pixar, which was essentially a software company, few years back, but Shutterfly, Snapfish, Flickr resulted in the closure of Kodak, which is the biggest recruiting platform in the world today. It is not some recruiting company. It is LinkedIn. FedEx essentially operates like a software company because they have to have extensive usage of software to work out their logistics, to work out their shipping routes, ensure optimal pricing, track each and every package. So the backbone of FedEx is essentially their software, not the hardware infrastructure around it. Pretty much the same applies to airlines. Budget airlines have come and flying has been democratized. So many people can afford to fly today as compared to how many could 20 years ago. This is not due to changes in aerospace engineering, not due to uh, new discoveries in aerodynamics. It is due to the underlying software which optimized the fuel consumption, which optimized the routes, the pricing, the kind of load that the aircrafts could carry, what it meant in terms of costs. So that optimization resulted in this. And fighter pilots, how do they operate today? That's another interesting example. Essentially, a fighter pilot today, he sends out a radar scan, and the radar looks at the skyline. It identifies where there are objects in the sky, and then the fighter pilot can zoom in on a particular aircraft and say, I want more details on this one. And there's a trade-off, of course. So the radar sweeps through the skyline, looks at all the objects, or it can zoom in on a particular object. Depending on what the fighter pilot chooses to do, there are trade-offs that he has to make. But even after the fighter pilot has zoomed in on a particular enemy aircraft, he can switch on something called situational awareness mode, which means he gets a lot more detail on the enemy aircraft, but he still needs to be aware of the other situation around him. So he makes compromises on what the scanning mode of the radar gives him, but he still gets a little bit of the situational detail. What are the other aircrafts in the vicinity? So if earlier he was scanning maybe a 80 degrees, he has to reduce that scan to 40 degrees so that the other processing capacity, the software can focus on details of the particular enemy aircraft he wants to zero in on. Once he has zeroed in on that enemy aircraft, if he can get it into something called a death dot, if he gets that enemy aircraft into a death dot and fires a missile, he has got the enemy aircraft. If he doesn't get it into the death dot, then he has to rely on his skills, because when it's in the death dot, the software helps him determine what is the lead required, what is the gravity drop required. So he doesn't have to rely on his flying skills so much anymore. So that's another classic example of how technology is completely changing the landscape here. Now, one of the philosophies of software earlier when we started programming with punch cards was that you had to determine the architecture, you had to write every line of code, punch it into punch cards, and then go through mainframes. Trial and error was simply too risky, but that has changed today. You can pretty much create software, throw it away if it doesn't work, unless it's in a life and death situation kind of software, but you can tinker around, and Unix emerged from this. So you do not have to follow a top-down waterfall model where the entire design is worked out and only then you get into coding. So that's also the very concept of agile software, that you can release software pretty much every day with small incremental delta changes. As we do this, consumers benefit more and more. One classic example that I take is one of the first cloud companies, Loud Cloud, software applications that it used to host for $150,000 per month. Today, that same software can be hosted on Amazon Web Services for $1,500 per month. So that's the kind of consumer benefit we are talking about. Now, if there is such a huge benefit for consumers, what does it mean for the producers? It means that the future of work will change because we will have outsourced the mundane tasks to machines. So it essentially becomes a consumer and producer utopia. If it seems like some dream world, think of it, how much writing and money, the other soft technologies, have changed human civilization. It's not unrealistic to assume that software will have such or even a much larger effect. So I'll talk about just some key points here and then we'll move to a specific example. certain unique attributes of software. If you want to create a physical product, you set up a factory, you get the raw material, you process it, there's a large capital outlay. But software has a very strange property. You can create high value software with almost practically zero capital outlay. Software programming, it's the labor that creates the capital. It's the labor that creates the value. And that's what makes software very different from engineering materials. If you were working in a factory and you kept experimenting with raw materials, wasting raw materials, the factory could go bankrupt. But if you keep throwing away code, this is not a problem. Waste in software, it's a feature, it's not a bug. Okay. Now, when you start treating this waste is a feature, not a bug, you start creating new functionalities, deploying new functionalities, fixing bugs as you come across them. Instead of starting with a full top-down design, you suddenly come across second order, third order effects that were never envisaged. Going back to the rideshare example I took, somebody started this app to order taxis without really envisaging all the second order, third order effects that will come. They could never have predicted that, which results in serendipity, finding things that we had never really envisaged, never really set out to do initially. Gmail had, so this results in a concept called perpetual beta. And Gmail, when it first started, kept experimenting with features until 2009. 5 years after it had launched, it was still in beta, and it had 30 million users by then. And the users could keep requesting new features, and Gmail would remain in beta mode. Even today, Google has a feature called Google Labs, where you can see what are the new features which are coming and play around with those. So this became the underlying philosophy rather than starting with a top-down design, because you could afford waste, you could afford to throw away code, you could afford to very quickly change what did not work. Because the product is the lab here. When we think of a lab, we think about AT&T, Bell Labs, beautiful building with a lot of machines. But today, it's the small digital product that's the lab. And some of the chaos is encouraged. Netflix actually uses a software called Chaos Monkey. So this Chaos Monkey randomly shuts down some of the production servers of Netflix and sees whether Netflix copes with this. Now, and it does this when Netflix is experiencing peak load, because they want to identify the bugs and uncover these very quickly. Imagine doing that on a shop floor when there's peak demand, shutting down some of the machines, because that has a tremendous impact. So that's where the software has to follow a different philosophy. And that's the philosophy Linux has also followed: release early, release often, and then quickly fix the bugs that you encounter. So I talked about feature, not a bug. Similarly, let's think if a car manufacturer, they come up with various prototypes. They cannot put every prototype into experimental mass production. But in software, you can. You can put a prototype into mass production. If it doesn't work, throw away and start with new code. Okay. Now I'm going to get into the specific example that I talked about earlier. The interface between IT and manufacturing. We hear a lot about Elon Musk's companies, Tesla and SpaceX. Tesla, as you know, electric cars, SpaceX trying to put people on Mars. These two companies are redefining what humans will do. But there is another company which doesn't get as much limelight. It is actually about redefining what humans will be in the future. There is this very famous quote: we don't have much of an understanding of the human brain. Some estimates say that if you were to consider the human brain to be 1 mile, our understanding of the human brain is so limited that we have covered only a few inches today. So developing an understanding of the human brain is very difficult, and that's where Neuralink comes in. Now think of some of the changes that we have encountered, the world as it was 50,000 years ago, and as it is today, language, technology, and the other changes. Now, many new languages have evolved, yes, but by and large, humans still speak today as they did several thousand years ago. Our biological bodies are still the same, so nothing much has changed there. A lot of the other things, technologies changed, but the human bodies have not changed. Our cognitive capacities have not changed in such a big way. That's where Neuralink comes in, trying to change this, to create a brain machine interface. What does that mean? If you have to create a brain machine interface, you have to capture outputs from the human neurons and you have to put inputs into the neurons, stimulating them. How does Neuralink go about this? This is where engineering comes in, and engineering becomes the limiting factor. Now, the human cortex, part of the brain, it has so many neurons and neural connections. If you have to interface with these neurons with, let's say, certain very, very tiny electrodes, you have to look at three aspects and trade-offs. And these three aspects are scale, resolution, and invasiveness. Scale is whatever technology you are using, is it giving you a full coverage of the brain, of the human brain? Resolution, how accurately, so spatial resolution is how accurately you are able to identify which neuron is doing what. Temporal, how accurately are you able to catch that neuron signal at that exact point in time when the neural fires. Invasiveness, whether you really need surgery for this interface. So there are various BMI tools today, and each has certain trade-offs. fMRI, how does it work? It tracks the changes in the blood flow. So based on the changes in the blood flow, you can identify, you can pretty much get a scan of the whole brain, which part of the brain has more blood flow, you get an idea. Resolution, you can see which parts of the blood is flowing through which parts of the brain at what point of time when which thoughts or actions are triggered. So you get an idea of which part of the brain spatially is responsible for which cognitive functions. But there is a lag between the blood flow and the actual neuron firing. So you can't identify the exact point in time when the neuron fired. And the fMRI is non-invasive. There's no surgery required. Come to the next step, EEG. You have recording electrical. So you put electrodes on somebody's head, non-invasive, like a helmet with electrodes. It has better spatial recognition, but the signals are distorted sorry, not better spatial recognition. It has better temporal recognition, but there is still a lag because the signal has to travel through the skull. Then there are certain other technologies which again involve some trade-offs, including implanting electrodes in the brain, and some of it is being done today with surgery. One of the experiments that has been carried out with BMIs, so some of the early experiments with BMIs, a monkey was given a treat when he had a particular thought. So what it would do is when a particular neuron fires, it would rotate a dial. That energy would rotate a dial, and that particular rotation of the dial would then give the monkey a treat. The monkey actually learned to trigger that thought in order to get the treat. That could be worked out. Now, in people with disabilities, most of the time, the motor cortex, the brain is working fine, but the spinal cord and the other nerves which serve as the middleman between the brain and the particular, let's say, he can't move his hands, then the damage is typically in the spinal cord and the nerves. that take the signals to the brain, but the brain is working fine. So what if you could have electrodes synthesizing this data and simulating the firing of the neurons, also providing a feedback loop? So let's say if somebody is trying to hold a cup, it's not as simple as just the neuron firing and getting him to move his hand to the cup and then close his fingers around the cup. He also has to have a feedback loop that, okay, now you have gripped the cup and you don't need to continue tightening your grip. So that kind of sensory perception has to be worked out, still being developed. Now, there is another very interesting experiment that was done with two rats, one in the US, one in Brazil. What they did is they linked their brain cortexes, and the rat in Brazil had two boxes. And there were two levers. Both the boxes were transparent. One of the boxes had a treat. So if he moved that particular lever, he got the treat. The other box had no treat. So he knew which box to open, the rat in Brazil. The rat in US got similar boxes. He had his brain linked to the other rat, but he didn't know that the other rat existed. But the boxes he got were not transparent. Now, the US rat, which could not see through the boxes, depending on which lever the US rat moved, the Brazil rat got the treat. So the US rat could not see what was in his two boxes, but if he moved the right box, the Brazil rat got the treat. If he moved the left lever, the Brazil rat did not get the treat. Because their brains were linked, they started operating together like one nervous system. And the US rat, which could not see what was inside the boxes, learned to move the right lever so that the Brazil rat could get the treat, because the pleasure sensations from the Brazil rat's brains were conveyed to the US rat. So that's another early experiment with BMIs. Now, if we take this further, in your implants today, we have this technology in a very rudimentary stage. You need to have about 3,500 electrodes to capture the full richness of sound of the human ear. We have about 16 today in the human ear implants. So still a long way to go. Retinal implants, if somebody is not able to see, probably a million neurons have to be triggered for excellent eyesight. But somebody not being able to see at all and somebody being able to at least see shadows and having hazy vision, probably a few thousand neurons. So some of these implants really life-changing. Where does manufacturing come in? Creating these electrodes, implanting them, reading these signals, getting them to talk to computers. These become essentially manufacturing engineering problems then. Now, there are, of course, a lot of challenges with implanting electrodes inside the human brain. One is you have to have really, to get the complete human experience, you have to maybe have 1 million or more simultaneously firing recorded neurons. That's where Moore's law comes in, something similar to Moore's law, if you're able to do as we do with transistors, with electrodes embedded in the human brain. And that's happening actually. The doubling rate is not 18 months, that's about 7.4 years right now, but it's changing. Then you have to have biocompatibility when you're implanting electrodes. You have to trick the brain into believing it's part of the brain so that the immune system doesn't attack it. You have to have wireless transition, signal amplification, and all of that, because you can't have wires sticking out of somebody's brain. And you have to find space in the brain to embed all this, so miniaturization. And just like the neurons, the electrodes interact chemically, mechanically, electrically, all of that has to be worked out. So all these engineering challenges have to be worked out. Now think of it over a period of time, if you're able to work all this out. We think much faster than we act. So human beings, to convey their learnings, to convey their experiences, to pass on knowledge to the next generation, we invented language. But to translate our thoughts to language, we're restricted by talking, reading, typing, listening. All of these are essentially compression decompression algorithms. And these result in data loss. One human being, whatever he's thinking, he just cannot convey it with language, 100% of it. So we are restricted by language. Video, yeah, it's an improvement. But what if you're able to communicate brain to brain, thought to thought? Yeah, not just through symbolic representations of thought. And then you have brains. Let's say if a group of engineers are building a massive bridge, they have to collaborate on, somebody has to work on the design, put it on paper, draw it out, all the engineering drawings, work through all the specifications. And there is data loss, there is misunderstanding, all of that has to be put on paper. But what if that whole communication happened brain to brain amongst expert engineers who are building this bridge together? So that's the potential for collaboration. And when that happens, our sensory organs essentially become just one set of inputs, but you have a digital brain where the experiences are information flow within the limbic system. So I know it sounds very spooky, embedding chips in the human brain, but that's what pacemakers would have sounded like a few years ago. That's what prosthetic limbs would have sounded like a few years ago. And that is could be one potential future here. And this is where the philosophy of software comes in, that you keep experimenting, you explore the frontiers of possibilities, and what a normal person, how does a normal person think? If it ain't broken, don't fix it. As engineers, we think if it ain't broken, it just doesn't have enough features yet. And in software, this is certainly more true than ever. So that's pretty much the conclusion. Thank you.
Thank you so much, Mr. Thakkar. It is a very nice description about the soft technologies, and you specifically mentioned that the software goes beyond the other soft technologies like the language. Beyond that, you have given nice examples, a large number of examples, but you have demonstrated that how the soft technology is bringing benefits to the society. Lastly, you have given an example of the neural link, cognitive intelligence model. So here, I do have one question regarding the cognitive skills and all. You have talked about the various types of the electrodes, trying to understand the functionality of the brain so that the models can be developed, models can be developed, that can be mimicked. The question is that the whatever may be the methodologies that you take up, the invasive or the non-invasive, it's about the EEG and other fMRI non-invasive methods and all. How good are they to capture the functionality of the brain, in the specific functionality of the brain, unless the exact functionality is properly captured, then the development of the cognitive model is that much accurate. If it is not accurate, then cognitive machines or the conscious machines can be, which people are now aiming at. So what is your viewpoint on that?
Yeah. So I would say this functionality still has a very long way to go, and which is why we are definitely not talking of. Sorry, you were saying something? Yeah.
So please go ahead.
Yeah. So yes. So today, this implanting these electrodes in the brain, it is definitely not being done for normal people. It can only be done on people who have disabilities and have a chance to improve their life with this. because there are risks involved. Technology has a long way to go, which is why we cannot as yet do that for people who have a larger downside from it compared to a potential upside.
Yeah, that's true. That's true. Let me see whether there is any questions in the chat box. Yeah, Professor Subir Majumdar has mentioned that a brilliant analysis and presentation. I also agree to that. Nicely described. Congratulations for Amish Thakkar. I would love to share this presentation with you.
Thank you.
It's true. Yeah, it's a very wonderful. I request the audience. Is that.
Okay. Yeah, there's a question from Dr. Dev Gupta.
So you can answer to that.
Yeah. Yeah. So you're talking about mass manipulation with Google and Facebook. Now, one of the tenets of software which I touched upon, one of the tenets of technology that I talked upon, and I'm not downplaying the negative sides of this, but if we don't allow experimentation, then we are also missing out on the potential upside. So yes, there are downsides, and yes, it seems like just the Uber example I took, something that seems like a very trivial app can become very powerful. Let me take another example. You mentioned Google and Facebook. Let me talk about Twitter. You would probably put it in the same category. Now think of it, Twitter, you have a functionality called hashtag. If you have a hashtag with a positive message and you have people getting onto the hashtag, within hours you can have good content created on a positive topic, something that would have taken years and the establishment of an entire publishing company without the software. Yeah. So simple functionality like hashtag in Twitter can pretty much be leveraged for creative agency rather than a destructive side. Okay, so I'm again, as I said, when you talk about not allowing this, you are also talking about losing out on this kind of an upside. So that trade-off has to be worked out.
I think there is no other questions in the chat box. We're also just in time. A question from Mr. Outdoor and impact of Uber is
Okay.
Okay, so Mr. Yeah, would you like to say something?
Yes. So you are saying that the third order impact of Uber, it's no different than the steam loco 2 centuries ago, airplanes a century ago, just faster. Okay. Now, whether it is the same or different, it's difficult to measure. But even simply taking your statement that just faster. Now think of it, when something moves just faster, compound effect, how it compounds exponentially over years. So when something moves a little faster over a 50-year period, over a 100-year period, then the impact it has is much, much bigger. Yeah. So that's where I talked about cognitive dissonance, where we tend to underestimate the impact in the long run.
Okay, so let us stop here today. Yeah. Thank you so much, Mr. Thakkar, for your presence and wonderful presentation. I'm grateful that you have agreed to our request and came forward to give a presentation at our platform. Thank you so much.
Thank you.
I request Prabhanjan to let us know about the speakers for the next weeks. Yeah, thank you. Yeah, Professor Devdut Sheikh. Professor Sheikh is a faculty in our electronics department. So Professor Sheikh will be talking about the machine vision for manufacturing. And then December 25th, Professor Feng Shu Gu from the University of Huddersfield, the vibration monitoring. Conducting a short-term 6 days training program on industrial robots from January 17 to January 22nd. Seats are very limited in number. So if anyone is interested, so all the webinars are getting recorded and it can be seen through the